when we want to do more advanced field theory, we need to learn about vector spaces, and not only vector spaces as you learned them in linear algebra, but a little bit more general vector spaces over a field. It's different, okay? In linear algebra, you learn about vector spaces, and you think they have vectors in them, and then you also think about scalars, which are typically real numbers, maybe sometimes complex numbers. But in abstract algebra, you want to talk about vector spaces over an arbitrary field. This field F could be any field, including a finite field. Finite field even with two elements, just 0 and 1. The field is sometimes called a field of scalars or scalar field, though that can be confusing if you happen to be both a math and a physics major, because in physics, they also have scalar fields, which mean something else. Okay, so we want to think about it in the abstract algebra way. What is a vector space? It's the V, it's not the F. The V is the vector space here, not the F. The F is sort of something external. It's an external scalar field, but they're related to each other. Vector spaces are abelian groups under addition. That's the exact same starting point for the definition of a ring, right? Rings are abelian groups under addition. And there is a second binary operation, you might say, but is it really a binary operation? Binary operations, as we've talked about them, like for groups, take an element of the Cartesian product of the group with itself and map it to an element of the group. Technically speaking, you take two elements of the group A and B, and you map it to what we call A times B. That's not exactly what's happening here. We can still maybe call it a binary operation, but if we do, we should realize it means something different. You've got, again, the vector space V in this external field F. For each scalar, A is a scalar in the field, and each vector V, this book doesn't bother with making the vectors boldface, notice, by the way, because it's like, why bother is sort of the attitude. Maybe it's the attitude you felt like, you felt like not putting little half arrows above your vectors. That attitude is now more sanctioned, that we won't bother with making special notation. Now, I might still do it. Yeah, just to emphasize that these things are different kinds of elements. There is an element A times V in V. So it's really something where you're taking this Cartesian product, V cross F, and mapping it to V. Give me a scalar A and a vector V. I can make an ordered pair AV. It's the elements, the components of the ordered pair are different. A is a field element. V is an element in this vector space, but I'm mapping it to something in the vector space V. I'm mapping it to AV. And yes, the field could be, for example, the real numbers. The field could be the real numbers, and A could, for example, be 2, and you'd be mapping 2V to the ordered pair 2 comma V to the vector 2V, which we know from linear algebra. And if you've taken some physics, geometrically, it can be interpreted as taking an arrow, if you imagine the vector to be an arrow, and stretching it, scaling it. That's why they're called scalars. Scaling it up by a factor of 2, making it 2 times as long. And we always write it like this. We write it as 2V. We never write it as V2, right? That would be confusing. The scalar is always on the left. Does it really have to be on the left? Is scalar multiplication commutative? Well, you could sort of allow for scalar multiplication to be commutative and allow yourself to write things like this, but it's just that we never do because it's just confusing. What properties does scalar multiplication satisfy? Distributive properties, 2 of them, in fact. This is a scalar being distributed over the sum of 2 vectors. A times the sum of the 2 vectors, V and U, V plus U, is A times V plus A times U. But you can also distribute a vector, so to speak, over the sum of two scalars. And the scalars being in a field means you can add them. A plus B and are both scalars here. B is a vector. We can distribute this vector through the parentheses there. There's two distributive properties. There's also an associative property, though realize this associative property, technically speaking, is a bit trickier. B times V is a scalar times a vector, which gives you a vector. And A times BV is a scalar times a vector, which gives you a vector. But on the right side, it's different. A times V in parentheses is not a vector multiplication. It's not a scalar times a vector. It's the product of two scalars, which, well, you're allowed to do because F is a field. That's the field multiplication there, giving you a scalar AB. Times a vector, that's the scalar times vector operation of the vector space. That's, in the end, a vector. These subtle things, you might say, oh, that's not a big deal, but they really are important to make sure you're not confused, right? You don't want to be confused. You want to try to dispel confusion. So thinking about these concepts clearly is an important part of that. Fields also have a unit, right? Definition of a field, commutative ring with unity in which every non-zero element is a unit. They also, I meant to say they have a unity. I get those words mixed up sometimes too. One is a unity, and 1 times V equals V. The scalar 1 times any vector V gives you that vector V. Is this saying 1 is the unity of the vector space? No, we don't say that. 1 is the unity of the field F, but it does kind of act like a unity in the vector space. But we don't really call it a unity because it's not an element of the vector space. Okay, so this is new. The field could be any field, including Z2, just containing 0 and 1, for example. What kinds of changes does having a broader definition bring into this theory of vector spaces? Well, we'll see here. And if you change the field, does it change the vector space? That's another question. The answer is yes, it can. It can change the properties that the vector space has if you change the field. Okay, you got your standard example. Example 1, Rn. Oh, save space, save paper, save a tree. Writing these vectors as a row vector instead of a column vector. Right, in linear algebra, you mostly think of these as column vectors, which is fine. And you might even say a good thing in linear algebra because we want to be able to multiply matrices times vectors. And it makes more sense to put the vector on the right and make it a column vector. So we have our standard definition of a matrix times a vector. If you thought of the vector as a row, then it's like it goofs up the definition of a matrix times a vector, unless you put the row on the right, on the left. It's a right to me, but it's left to you. Unless you put it on the left. You know, you can do that, right? You can multiply a row vector times a matrix and get a row vector out as well. But we're just used to doing it with column vectors. Anyway, in an abstract algebra class, there's no need to bother. At least at the moment, we're not doing any matrix multiplication. So write it as a row vector, n tuples. Rn means the components or coordinates, if you prefer, of the ordered n tuples are real numbers. This is Rn. This is something you're used to. You add vectors component-wise, and you multiply by a scalar. B is a scalar component-wise. No problem here. B and the A's are all real numbers. There's no problem writing this BA1, BA2, etc., because you're just multiplying real numbers. You might wonder, though, could I change the R to an arbitrary F, an arbitrary field, and consider ordered n tuples of arbitrary field elements? And is that a vector space? Same operations? Yeah, it's still a vector space. This is a vector space over the reals. You always say what the field is here. You want to get in the habit of saying what the field is. This is over R. If we did that more general case, it would be over F. You always emphasize what the field is by saying the vector space is over the field. A little bit strange terminology, but it's what we're stuck with. Example 2. M2Q. Set of 2 by 2 matrices with entries from Q is a vector space over Q. Q is the rationals, quotients. That's why we call it Q. Any Star Trek fans here, like including older Star Treks? Okay, there. You should look up some old Star Treks. Okay. There's a famous sporadic character in the old Star Treks. Maybe I haven't watched the newer ones. Named Q. Okay. And Q is not a very nice alien. Oh, he sort of thinks he's God. And he kind of is like God in the story. Anyway. I just think of that when I think of Q. We can add matrices and we can multiply them with scalars, component-wise. There's nothing special about using Q here. We could have used R. Matrices are vectors in this example. What other examples do you have in linear algebra? Well, okay, let's continue with these examples, but we'll talk about linear algebra a little bit too. ZPX, we've seen this before. That's the ring of polynomials mod P. Coefficients in ZP is a vector space over ZP where P is prime. Why does P have to be prime? So that ZP is a field. But when you think about this, you're only thinking about adding the polynomials, not multiplying them. Of course, we can multiply them. We know that is a field in its own right where you can multiply polynomials. But when you're thinking of it as a vector space, you just kind of ignore that. But we can multiply by scalars, numbers, which we really are thinking of as being numbers here instead of constant polynomials. Because they're elements in the true ZP, they're technically numbers, 0 through P minus 1, instead of constant polynomials. Is it a big deal making that kind of subtle distinction? Maybe not, but we want to be technical about it. See, this is the field of complex numbers. It's a vector space over R. If you think of the complex numbers, the individual complex numbers, A plus BI as being the vector space elements, almost like it's an ordered pair, right? Is there much difference between thinking of a complex number in this form and thinking of it as an ordered pair? Could we do this? Yeah, you can. Though what gets confusing if you think of complex numbers as just ordered pairs, it gets confusing is when you actually multiply complex numbers in the usual way. That gets confusing. But here in this example, we're not multiplying but two complex numbers. We've got a real number. This is a complex number. We've got a real number times a complex number. How do you do that multiplication? Well, you multiply the real number times the real part and the real number times the imaginary part, and you get this complex number. Of course, that is the same as the ordinary multiplication of a real number times a complex number. That's nothing different that we're doing here. We're just saying that's the external field that we're thinking about as being our field of scalars. And yes, coming back to examples from linear algebra, in linear algebra, you see examples like this, typically written Pn. Remember what that was? That was the vector space of all polynomials, not of arbitrary degree, but degree to less than or equal to n. That's definitely not a ring or a field, because if you multiply two polynomials of, say, degree less than or equal to 3, you're going to get, in general, a polynomial of degree 6. This is the vector space of all real polynomials, meaning real coefficients of degree less than or equal to n, where it's assumed here when I write this that the field is R, the real numbers. We're adding polynomials and we're multiplying them by scalars. We're not thinking about multiplying the polynomials. Of course, you can multiply polynomials. You're just ignoring the fact that you can. You also may remember, I hope, and this comes up in numerical analysis, vector spaces like this. CAB. What's that? I won't write it out, I'll just say it. That's the vector space of all real valued continuous functions on the closed interval from A to B. C standing for continuous. We use this notation in numerical analysis. The vectors in here are functions, not just polynomials, any function that's continuous on this closed interval. I also said real value. Does it have to be real value? Technically not, but that's the usual way people think about this. Could be complex values, for example. The outputs of the functions could be complex numbers. Why is it a vector space? It does satisfy all these properties. It is an abelian group under addition. You add two real valued continuous functions on the closed interval from A to B, you'll get such a function. Function addition is commutative. There's a zero function, which is continuous. Output is always zero. There are additive inverses. You got a function. What's its additive inverse? We'll just take its reflection across the horizontal axis. It's negative. And you can multiply such functions by scalars, and these properties all hold. Very quickly, the author transitions into some fundamental things that took you a long time to understand in linear algebra. Subspace, linear independence, spanning, and basis and dimension. The most important of those being ultimately basis and dimension for us. First of all, a quickly definition of a subspace. It's similar to subgroup, subring, that kind of stuff. If V is a vector space over a field F and U is a subset of V, we say U is a subspace if it's also a vector space over the same field under the operations of the vector space, just like the definition of a subgroup or subring. It is a subset that is a group or a ring itself with the same operations. So with subspace, it's a subset that's a vector space over the same field, same operations, same way to add vectors. And in linear algebra, you learn about examples like, R2 can be visualized as the plane. And non-trivial proper subsets include, well, just the origin by itself, the trivial vector space, a one element vector space, and any line through the origin. Either thinking of the elements as being points or as vectors, as arrows, if you prefer, column vectors, that ends up being a subspace of the plane. In three-dimensional space, I'm going to draw essentially the same picture, but now you need to imagine it three-dimensionally. So these are axes sitting inside three-dimensional space. Examples of proper subspaces include, again, just the origin, any line through the origin, any plane through the origin. That's supposed to be a plane through the origin. Sitting inside three-dimensional space will be a subspace of R3, a proper subspace. Of course, there's the entire space itself as a subspace of itself. What do linear independence and spanning mean? Well, it's just a definition of linear independence right here. A set of vectors is said to be linearly dependent, first of all, is defined first. Over the field F, that's different here. So in linear algebra, you just say this set of vectors is linearly independent or linearly dependent. You're not worried about being extra careful about the field because the field is almost always the real numbers. Here we're emphasizing there is a field. They're vectors from S. This set of vectors is going to be linearly independent if there are scalars, not all zero. so that this linear combination of the vectors is zero, the zero vector. And if you can't find such non-zero scalars, then it's a linearly independent set. Typically in linear algebra, you say the set of vectors v1 through vn is linearly independent if this equation being true means the a's are all zero. Why was this important in linear algebra? It was related to solving systems of linear equations, for example. Are the column vectors of your coefficient matrix linearly independent or not? If they are linearly independent, then there's only the trivial solution of that homogeneous system. If they're not linearly independent, there are non-trivial solutions. You're going to have free variables. This is what went on in linear algebra. A basis is a subset of the vector space that's linearly independent over the field, and every element of the vector space is a linear combination. That essentially, that last phrase means that the basis spans the vector space, but that's not stated here. And these things are called linear combinations. Here you're saying every element of the vector space is a linear combination of those basis elements. So in R2, for example, there's the standard basis. Writing them as column vectors would be this one. Standard basis of two elements. These are linearly independent. We say in linear algebra, we say, well, they're not geometrically, they're not parallel to each other, right? You draw them as arrows. They happen to even be perpendicular or orthogonal in the plane. And they do span the plane. Any vector in the plane is a linear combination of them. And you wrote things like this. R2 equals the span of those two things. But that's not the only basis of R2. In fact, I hope you remember that any two non-zero vectors that are not parallel, not scalar multiples of each other, form a basis for R2. Any two vectors in R2, always say like 1, 4 and -2, 17. Those are two non-zero, non-parallel vectors in the plane. Therefore, they do form a basis of the plane. That was the basis theorem. Other ways to think about it is if you make this into a 2x2 matrix, it's an invertible matrix. It's determinant as non-zero. Good to think about those kinds of things as well. Why do we need vector spaces? Well, it comes ultimately to this theorem here and a definition. Invariance of basis size. If U1 through UM and W1 through WN are bases of a vector space F over a field, then in fact, the number of elements of the basis has got to be the same, and that has to equal n. And that's then allows us to define dimension of the vector space. A vector space that has a basis consisting of n elements is said to have dimension n. The trivial vector space is said to be spanned by the empty set and has dimension 0. Just a definition, because it kind of makes sense to call it dimension 0 because it's just a point is the idea. Doesn't have a basis, though. The trivial vector space does not have a basis.